Hello. Welcome to our presentation, Increased Hematopoietic Stem Cell Yield through Controlled Oxygen Conditions Continuously During Isolation and Expansion. On behalf of Biospherics, I'm your host, Ray Gould, and look forward to joining you today. So let's begin. In the U.S., there has been a long-term trend of a growing number of hematopoietic stem cell transplants performed each year. And in their 2016 report, Current Uses and Outcomes of Hematopoietic Stem Cell Transplantation, Dr. Anita D'Souza and colleagues of the Center of International Blood and Marrow Transplant Research report that over the last 25 years, the number of hematopoietic stem cell transplants, both autologous and allogeneic, performed annually has increased fivefold. This tremendous increase in the number of transplants performed has resulted in extreme demand for sufficient quantities of therapeutically viable stem cells. However, a significant gap exists between the available number of hematopoietic stem cells and their current supply. First, this has been the result of limited expansion potential and has resulted in low HSC yield. Second, high rates of apoptotic cell death in donor cells gives rise to low rates of engraftment. And finally, these factors plus an insufficient number of donors, especially in cord blood therapies, have led to the gap between supply and demand. Further, these factors have produced massive cost burdens on our healthcare system and have diminished the therapeutic potential of hematopoietic cellular transplantations. Ultimately, this means that fewer patients have access to the life-saving potential of these important therapies. 2017 figures from the American Cancer Society estimate that there are nearly 173,000 new cases of blood cancer in the U.S. each year. And with an estimated 1.3 million people currently in the U.S. either living with or in remission from leukemia, lymphoma, or myeloma. Significant strides have been made in advancing the effectiveness of treatment options for blood cancers, and surveillance data from the National Cancer Institute shows steady improvement in 5-year survival rates over the period of 1960 to 2012 for patients with leukemia, lymphoma, or myeloma. However, what if we could do significantly better? What if we could accelerate the cost reduction for administering HSC transplant therapies? Would more patients be able to access these therapies? What if we could dramatically improve therapeutic outcomes? Could we impact our current 5-year survival rates? Could we create a scenario where more third-party payers provide reimbursement? Imagine, if you will, a scenario where the gap between hematopoietic stem cell supply and HSC demand no longer exists, where greater HSC expansions permit sufficient cell yields. Further, I ask you to imagine a setting where reduced apoptotic cell death means that more therapeutic cells engraft inside the patient, where abundant numbers of therapeutically viable stem cells mitigate the need for multiple cord blood donors. How would you accomplish this better version of your current work? Perhaps we look to other industries, like manufacturing, for guidance, where the implementation of quality principles is standard practice and effective for reducing the cost enhancing the quality and improving the consistency of manufactured products. When we examine the cell culture or live cell industry, I ask, where are the total quality principles? In a research setting, there are, of course, good laboratory practices, or GLPs, and even good cell culture practices, or GCCPs. And further, in the regulatory or manufacturing space, there are GMPs. However, even these guidances lack fundamental, basic, and logical considerations for the needs cells have during incubation and handling. And what do I mean by that? Well, when you view a cell culture lab, what do you see? There are comfortable chairs, open tables, and benches. There are incubators which open and close into the room, and even machines or devices located in the open room. While this type of lab design is quite normal, it's really designed for people, not cells. And for the remainder of this talk, I will refer to this type of laboratory as a people-centric lab because its design and function places greater emphasis on the needs and conveniences of human beings versus the actual needs of cells. And what are the actual needs of cells? Well, they are needs which have been historically and completely disregarded by nearly every single cell scientist. These are needs which are impossible to meet in a lab where people-centric incubators, hoods, cabinets, benches, machines, devices are present. For addressing this, I propose a set of 5 total quality principles aimed at meeting the needs of cells. These needs have been overlooked in nearly every cell culture lab in the world. These are principles that, when applied, as would be normal in any other industry, provide a method for reducing the costs, enhancing the quality, and improving the reproducibility of generating data and producing experimental outcomes. First principle is that cells need physiologic simulation. Next, they need optimal conditions full-time. Third, they require full-time protection. Fourth, cells have unique protocol needs. And finally, they have needs which account for the dynamic nature of their in vivo environment. And when combined, I'll refer to these total quality principles as cytocentric. A set of principles which moves the previously unmet needs of cells into the foreground and makes those needs a primary consideration in the methods for incubating cells, handling cells, and even the observation and analysis of cells. While all of these principles are important, for the purposes of our time together, we will focus only upon the first 3 in the context of hematopoietic stem cell research. First, let's examine physiologic simulation. In the November 2016 publication of Nature Review's Drug Discovery titled Screening Out Irrelevant Cell-Based Models of Disease, Dr. Peter Horvath, distinguished professor at the Institute for Molecular Medicine, Finland, and co-founder of the European Cell-Based Assays Interest Group. Together, he and his colleagues outlined several considerations for performing physiologically relevant cell-based research. Much effort and sophistication has been developed for many of these. A multitude of companies, products, services, even entire industries have been created for the purposes of utilizing better tissue models, working with a more appropriate genomic or genetic profiles, even using mixed cell models, further using physiologically appropriate medias, and finally incorporating relevant vessels, substrates, and surface options. However, when we look at the atmospheres in which cells are incubated, handled, and imaged or observed, the atmospheric conditions of 37 degrees Celsius and 5% CO2 have remained virtually unchanged at physiologically irrelevant levels for the last 100 years. So is it even possible to supply physiologically relevant cell conditions in a traditional people-centric lab? Furthermore, what is a physiologically relevant atmosphere for incubation and handling of cells? Well, for most cell labs, simulating physiologically relevant atmospheres begin with addressing a widely neglected variable, oxygen. Even though room air levels exist at roughly 21%, there is no cell in the human body which experiences oxygen levels anywhere near this amount. In the body, oxygen levels exist in ranges and gradients, and 21% oxygen is immediately reduced in the pulmonary system and can range anywhere from 10 to 15% oxygen. As oxygen is exchanged into the circulatory system, levels can range from 13% in arterial blood all the way down to 5 to 10% on the venous side. And bone marrow levels can range from 6% to as low as 1%. All other tissues in the human body can range anywhere from 5% down to 1% and sometimes even less. And the actual oxygen percent that any cell experiences really depends on its distance from the blood vessel source. As oxygen is released by the capillary, it diffuses through the tissue and it's consumed by cells along the way, thereby establishing an O2 gradient as it travels. So most tissue sites in the body exist at oxygen levels 5 to 10, even 20 times less than what is routinely performed in cell cultures in room air conditions. So is it even possible to supply a cell's need for physiologic simulation? No. Physiologic oxygen is never found in room air, and it's impossible to simulate in traditional people-centric labs. Even in the rare instance an incubator is outfitted with oxygen control, most units do not permit control at levels which match a number of tissue sites, extreme low oxygen. Next, let's take a look at the total quality principle. Cells need full-time optimization. Perhaps you've taken some first steps at simulating physiological atmospheres. Yes, you've even tried work with physiologic oxygen in your cell-based approach, and you've thought to yourself, I do my best to work quickly and efficiently in the hood. Or perhaps you've said, my cells are only out of the incubator for a few minutes, and you've asked, does it matter? Do these changes or excursions into room air matter? Or even what's the big deal? So what? Or perhaps you've stated that cannot have much effect on my cells or my data, right? The following should be helpful for addressing these sentiments and statements. In their 2006 Nature publication, Dr. Jacques Poussager and colleagues report that HIF1-alpha, a master transcriptional factor with regulatory roles ranging from gene expression to cell proliferation, from cell survival to metabolic function, from role in tissue regeneration to human development, they report that HIF1-alpha has an extremely short half-life compared to other cell proteins. Further, they report that this critical protein destabilizes in less than 5 minutes when exposed to room air oxygen levels. More specifically, for hematopoietic stem cell biology, in their 2015 publication in Current Opinion in Hematology, Dr. Hal Broxmeyer, distinguished professor at University of Indiana School of Medicine and pioneer in the field of cord blood stem cell transplantation, he and his team described the damaging effect on hematopoietic stem cells by even brief exposures to room air oxygen. The team reports that even these short durations which were as little as 10 minutes, resulted in irreversible effects that resulted in the loss of HSC numbers. Further, the team reported that these exposures were accompanied by rapid production of reactive oxygen species, or ROS, which mimicked ischemia reperfusion injury. This response is so damaging to the HSCs that the team termed this phenomena extraphysiologic oxygen shock or stress, or EFOS. Imagine the incubator in your laboratory. You place your cells inside and the experimental conditions remain constant without interruption for the duration of the experiment, right? This is highly unlikely the case. It's more likely that your experiment shares an incubator with several other experiments, resulting in opening and closing of the incubator door multiple times all day long. Opening and closing the incubator door results in uncontrolled changes in cell parameters like temperature, CO2, pH, and oxygen, and this is a major source of variability. Nobody reports in their methods section cells were cultured under randomly fluctuating and suboptimal incubator conditions for 12 hours or 24 hours or 48 hours, yet this type of approach is normal practice in most cell experiments. Further, think of what happens to cells when they leave the incubator and travel to the BSC or hood for handling. Everything changes. Temperature, CO2, pH, and oxygen all swing to suboptimal levels. The amount of time involved depends. It depends on the skill of the technician. It depends on the difficulty of the procedure. It might depend on whether the phone rings or whether he or she receives a text, a tweet, a Snapchat, or Instagram message. These factors introduce more sources of variability. Certainly, we can agree that traditional people-centric labs are not capable of supplying optimal cell conditions full-time, right? So is there any good news for your cells? Any good news for your HSCs? What would it take to combat these problems? If you were able to apply a set of total quality of principles in your lab for reducing costs, for enhancing quality, and improving the reproducibility of your data and experimental outcomes, what would you do? What would it look like? Well, it would mean taking incubators, hoods, procedures that are routinely performed in people-centric labs where HSC exposure to toxic and variable room air oxygen is disregarded, and bringing these equipments, incubators, hoods, machines together in a continuous workflow where cells receive controlled conditions full-time without disruption or variation. It's a laboratory alternative designed specifically for fulfilling the unmet needs of HSCs, while permitting the same comforts and convenience found in traditional people-centric labs, where physiological atmospheres for stem cells, CO2, temperature, pH, and oxygen are simulated continuously during incubation, handling, observation, or analysis, and accomplished through design features which conform to total quality principles. It means use of closed incubators that are connected to closed hoods, and closed hoods which are connected to one or more individually controllable closed incubators. Closed hoods which can enclose any third-party machine which is part of your experimental workflow. And these can range from any microscopy or imaging setup to analytical machines like the XF analyzer from Seahorse or Agilent, or the Xcelligence series from ASEA Biosciences, or any cell processing machine, meeting any throughput requirement, which can range from manual scale all the way to high throughput scale, necessitating the use of robotic or automated platforms. So these total quality principles are logical and make sense. But is there any data supporting these concepts and ideas? What happens when these principles are applied to hematopoietic stem cell biology? Is there any evidence that it provides benefit? In their landmark publication, the June 2015 journal Cell, titled Enhancing Hematopoietic Stem Cell Transplantation Efficacy by Mitigating Oxygen Shock, authors Dr. Charlie Mantell, Dr. Heather O'Leary, and Dr. Hal Broxmeyer report the effect of supplying physiologically optimal oxygen conditions in mouse HSCs, conditions which were maintained continuously during collection, through isolation, to expansion, and then finally maintained through transplantation without disruption or variation. And the authors report that HSCs incubated and handled using this new method resulted in a 3 to 5-fold increase in cell yield versus cells cultured or processed using the old method. Further, the team reports that not only was there dramatic increase in cell number, but that transplanted HSCs also resulted in significantly greater stem cell engraftment rates versus those transplanted following traditional methods. If that wasn't enough, there's an added benefit to closed incubation, handling, imaging, and analysis. In the body, cells receive full-time protection from contamination via the immune system. So cells need full-time protection. However, in an open lab setting where enormous bioburden exists, how can cells be kept free from contamination? Is it even possible using traditional methods for incubation and handling? Incubators open directly into rooms where people constantly breathe, cough, sneeze. And these occurrences represent the biggest risk for sample contamination. Even though open BSCs and hoods afford some protection during HSC handling, objects placed inside the hoods or cabinets create turbulence and disrupt laminar airflow. Likewise, a technician's arms and handheld devices introduce more turbulence. Turbulence which permits a surface contaminant to become airborne and contaminate your sample. Thus answering the question with an emphatic no about a people-centric lab's ability to provide full-time protection for hematopoietic stem cells. A cytocentric lab places a physical barrier between the dirty lab and its biggest source of contamination, people. And it never permits room air inside. The cell atmospheres are created using high purity, medical grade gases which are continuously HEPA filtered and provide full-time protection. This means for over 8 years at Biospheric's R&D facility, which is located in the middle of the factory floor, samples grown in our testing unit have remained contamination-free, exhibiting no colony-forming units, and has been accomplished without the use of antibiotics. This concludes our presentation on behalf of Biospherix. It's been great joining you today. If you're ready to discuss your hematopoietic stem cell application, please contact us in the U.S. at 1-315-387-3414 or by email at sales@biospherics.com. Mention the word hematopoietic and receive a $250 discount on your purchase. Thank you.